Let's take a look at writing chemical formulas. So I've showed you how to write chemical names. That's these things right here, the long written out forms. But this is the chemical formula for this chemical name. And so we're going to try going the other way. Given the chemical name, nitrogen dihydride, what is the chemical formula for this substance? So what is this thing for nitrogen dihydride? So let's look at how we do this. So nitrogen on the periodic table is N. Hydride is hydrogen. So we've got hydrogens. Now we want to look at our prefixes, which are going to indicate how many of these things we have. Because there's no prefix here, this must mean mono, meaning there's only one of these. The prefix here is di, which means two. So we've got two of these. So our chemical formula for nitrogen dihydride should be NH2. Let's take a look at ionic compounds. I'm going to give you an attempt or a chance to try this on your own in just a second. So for ionic compounds, you have chemical names and you have these chemical formulas here. Now, the weird thing with ionic compounds is there's no prefixes, right? So it doesn't tell us how many atoms there are. So there's a 2 here, but it doesn't say it's dichloride. We don't know that. So we need to figure out how we figure out what number goes there. So how do we know what number gets placed with each atom? Because we have no prefixes. So in order to do this, we need to look at the charges. We're going to look at the charges on the ionic compounds. So the charges on ions dictate the number subscripts. So for magnesium chloride, the reason that we know these numbers, so for MgCl2, the reason we know this is a 2 is because magnesium on the periodic table has a 2+ charge and chlorine has a -1 charge. In order to make this whole compound neutral so that the magnesium charges and the chlorine charges add up to give us 0 charge, we need 2 chlorines. So if we think about it that way, it makes a little more sense. So we've got 2+ and we had a 1-, and in order to make these even out to 0, add up to 0, we need to have 2 of them. So we've got 2+ and then 2 minuses as well now. And so that gives us this charge, which is why we have 2 chlorine atoms for every 1 magnesium atom. So when we go to write our chemical formulas from a chemical name for ionic compounds, this is ionic compounds, some things that we need to remember when we're doing these is that our cation, the metal, always goes first. And then the anion, which is the nonmetal with the negative charge, comes second. So we can see that in our magnesium chloride. Magnesium has a 2+ charge, so it goes first. Chlorine has a 1- charge, so it goes second. Right, and then these numbers on these elements are determined by ion charge. We've learned that. Let's look at some other examples here. So magnesium chloride, we've done that one. Let's look at lithium sulfide. Lithium is Li. Sulfide indicates sulfur. Now on the periodic table, lithium is in our alkali metals. It's in group 1. Sulfur is all the way over here. It's under oxygen, sulfur, and it's in group 6, 7, 8. So in order to achieve an octet, it's going to gain 2 electrons. So sulfur has a -2 charge on it. Lithium will want a +1 charge. +1, -2. So what we want to do is we want to take those charges and see how we can make them add up to 0. So we need 2 plus 1 charges plus our -2 equals 0. So we need 2 lithiums in order to equal out the charge of the sulfur. So we'll have Li2S in order to get our charges to equal 0. I'm going to show you a shortcut on how to do this. You can preview it over here in order to make this a little easier, but I want you to understand why we're doing this. I always like you all to understand what we're doing and not just accept the shortcut. Let's take a look at potassium phosphide. Potassium is also an alkali metal. It's a little bit underneath lithium. It's lithium, sodium, then potassium. The symbol for that is K. Phosphide is under our nitrogen over here, P. It's in group 5, or 15A. So it needs to gain 3 electrons to become an anion that has 8 valence electrons. So it's going to pull in 3 extra electrons to fill its octet. So we have potassium, which is in group 1, so it's a positive 1. And then our phosphide, which is going to form a -3 charge. So we're going to combine these, and we know that we need 3 potassiums in order to equal out the charge of the phosphorus. So K3P is how you would write this one. Let's take a look at the shortcut now. I'm going to clear all the pen markings, so make sure you have everything down that you want. Here's the shortcut over in this box. So I call this drop and swap. What we do here is we figure out the charges on the elements from the periodic table, and then we take their charges, we drop them down, and we swap them, and those are the numbers that go with the ions here. Let's take a look at our magnesium. Magnesium and chloride. So this was a 2 plus, 1 minus. So if you apply the drop and swap principle, you drop it, you swap it, drop it, and swap it. You end up with 1 magnesium and 2 chlorides. Simple enough. This over here is a little bit more complex example because we have lead and oxygen. If you'll notice, lead is a +4, oxygen is a 2 minus. What I wanted to demonstrate here is that when you're writing chemical formulas, you do need to have the smallest number on them. So here you would think it would be 2 and 4 if you did the drop and swap principle, but because these are even numbers and we can reduce these to a smaller number, you're going to end up with lead, 1 lead and 2 oxygens. So PbO2 is the correct formula for this one. So make sure if you happen to have even numbers, this won't happen very often, that you do reduce them. Most of the time it will be an even and an odd. Okay, or 2 odd numbers, sorry. If you have like a 3 and a 3, make sure you take it down to 1, that sort of thing. So, yeah. And also we never write ones. If you'll notice, there's no number 1 here. We don't put ones as subscripts. If it's a 1, we just assume that it's not written, okay? So here's a reminder of how you determine ion charges. These ion charges are based on the group location where the atom is in the periodic table. These first row alkali metals like to form a +1 charge because that's how they achieve an octet, is by losing that 1 electron, valence electron. The next group does a +2. Oftentimes over here, you're going to be using your halogens a lot. They like to gain 1 electron in order to achieve an octet. These guys gain 2. These gain 3, which is why they have the charges that they do. These can be a +4 or a -4. And these are a +3 charge when they become ions. Do be aware that these charges that I'm showing you on the periodic table are only used for ionic compounds. If there's a molecular compound, there's no charges because they're sharing electrons, they aren't losing them. So ionic compounds have charges because they are not sharing electrons, because they're losing and gaining them. So make sure you're clear on that point there. Okay, so let's give this a try here. Take these chemical formulas and make write the chemical formulas for these ionic compound names. So use the periodic table down here in order to find out the chemical formula for calcium chloride and iron 3 oxide. Remember, you're going to need to find the charges on these, and you're going to need to cancel the charges out, or you can use the drop and swap method to determine the numbers of each atom in the chemical formula. All right, let's take a look at calcium chloride. So calcium is here on the periodic table, meaning it's going to be a +2. Chloride is here on the periodic table, meaning it's going to be a -1. We're in group 7 here. I did kind of cut the noble gases out because they don't matter right now for what we're doing, and I need the picture to be bigger. All right, so calcium, Ca, chloride, Cl. We've got a 2+. Chloride is a -1. So if we use our drop and swap method, we find out that we've got calcium, Cl2. CaCl2 is the formula for this one. Iron 3 oxide. Iron's here, so it's Fe. Oxide is here. It is in this group, so it wants a -2 charge, -2. And iron, you might be like, oh, well, what's the charge on iron? It's a transition metal. It can have multiple charges. That's the charge on it right there. That tells us that this is a 3+. That's how we know. So we're going to drop and swap our charges in order to figure out the subscripts on these. So it should be iron 2O3. If you think about it charge-wise, this makes sense. So we need 2 Fe3 pluses, because that gives us 6+ in order to even out our 3O2 minus. So that would give us a total of +6 on the charge and -6 on the charge, which gives us an overall charge of 0, which is what we're looking for here. So that would be your final answer for each of these. Let's take a look at polyatomic ions. This is the last thing we're going to cover during naming. It is something that you're going to run into a lot. We use these chemicals all the time. So polyatomic ions are ions that contain more than one ion, or more than one atom, sorry. So polyatomic ions contain more than one atom. Sorry, these are ions that contain more than one atom. That's what a polyatomic ion is. So we can see that here. We've got this compound thing, but it's got a charge on it. You aren't used to seeing that. You're used to seeing NO3, no charge. But some compounds have charges, and we call those polyatomic ions. You will be given this list of polyatomic ions for exams, so you don't need to memorize them, but you do need to know how to use them. And I would advise kind of being familiar with these so you can find them quickly, because on exams, you're going to need to know how to do this quickly. So it's not going to hurt for you to be familiar with them or try to memorize them, just so you can be quicker on an exam. If you'll notice, these polyatomic ions have different charges. Some of them have a -1, some of them have a -3, some of them have a 2-. Some of them have positive charges. So you will need to be aware of that as you're working. Let me show you an example of how to use these. So Na3PO4, if we wanted to name this compound, we go here and we find sodium. So this would be sodium. And PO4 is right here. So it's phosphate. So this would be sodium phosphate. If you'll notice, I didn't change this to an "ide" ending. This "ate" and "ite" are already their own endings, and they do indicate that we have a polyatomic ion. So make sure you aren't changing that ending. You just copy it straight to the name. Let's look at making a chemical formula from a chemical name. So we've got magnesium hydroxide. Magnesium is here on the periodic table, so it's Mg. Hydroxide is right here, so it's OH-. Magnesium is a +2. So in order to figure out what subscripts we need, we're going to drop and swap. So we end up with Mg OH2. Notice how I put this in parentheses here? That's because the entire OH thing is duplicated. So if you looked at this ion, you would see the magnesium 2+ here, and it's going to be associated with, not chemically bonded to, an OH- and a second OH-. So I put the OH in parentheses to indicate that there are 2 of those compounds that are associated with the magnesium. So make sure you put parentheses around stuff whenever you're putting subscripts so that you know that it's referring to the entire polyatomic ion. Okay, give this a shot on your own. See if you can name this chemical compound and write the molecular formula for this chemical compound using the tools that you've been given. Let's take a look at the answers here. So CaCO3 is calcium. So calcium, CO3, right here, carbonate. It's that simple for polyatomic ions. Potassium carbonate, here's potassium, so it's K. Carbonate, we know it's this one. Potassium is in group 1A, so it has a +1 charge on it. This is a +1, +2 is here. CO3 has a 2- charge. 2-. So in order to figure out the subscripts on these, we're going to drop and swap. We find out that we need 2 of our positive potassiums in order to cancel out the charge of our single carbonate polyatomic ion. So there will be 1 carbonate with a 2- charge, and it will be associated with 2 potassiums in solution. Okay, so that's how we use polyatomic ions in naming. So that's the end of topic 2. Let me know if you have any questions.